recording. So this is one of those just came on today morning. So there is a very rare transit of the one of moons of Saturn, right? And I don't think that unless you have a larger 10-inch telescope that you can observe it, but this is just for your information to get you an idea like what kind of thing is it. So as we learned about the planets last 2 days ago, this is Saturn, and remember we discussed that there are around 210 moons orbiting around these planets, right? And remember that we talked that the Saturn also has some planets, and there is one planet called Iptis right here, one moon called Iptis that is going to transit around Saturn in tomorrow and day after tomorrow. And so you probably don't know about what a transit means, so let me explain it. So it's not something like that you don't know, it's just the word, right? And here is the moon, Saturn's moon, which has a 1,460 kilometers in terms of diameters. And we used to tell that this has a dual personality, right? So what that means is one hemisphere is covered with bright ice, and the other side is darker material, right? So these are images taken from NASA Cassini orbiter, right? It is this moon that we are talking about today. And so a transit means that on July 17th at about 9:12 UT. UT means the universal time. So these are different systems that we use to keep time, especially in astronomy. So the universal time means everyone has a one time in that time frame, right? So this is, as far as I remember, this is somewhat around 10 hours behind us. But however, you can search in the internet and take the UT time, right? At any time. So this particular moon will make first contact with the northeastern edge of the outer ring of the Saturn at this particular time. And so how it looks like is something like this. You can see that compared to the Saturn, how tiny is this particular moon right here from this black dot, right? So this is how it starts, and then it's going to continue to transit. Transit means it goes in front of the planet Saturn. So which means if you observe the Saturn at this particular time, you should see a small black dot in front of Saturn at some point, right? And so that's what a transit means, right? So normally we use this transit technique to detect exoplanets, planets around the other solar systems. We will discuss about that as well later. And here, so this is what you will observe. What the problem is, if you have a smaller telescope, you can observe Saturn, but the problem is this particular moon is even very tiny. So which means you have to have a very clear skies, and at the same time you should have a little bit larger telescope. So I would think that it should be at least a 10-inch telescope. So the 10-inch telescope means a relatively larger telescope, which is hard to find in a country like Sri Lanka. But if anybody is interested and just need to look at it, just try to see whether you can see something here, right? And as astronomy is actually an observational science that you never know what would be observed, right? Sometimes you assume that you cannot observe anything and suddenly you can observe it. I mean, that has happened to us many times. So It's always helpful to observe it. Right. And so that's just for your information. And I can't remember whether I have shown you these latest images from James Webb Space Telescope. Right? So I may or may not have, but let me just go with that. This is, so I think this took all over the news in the past few days, but let me explain you something extra and why these images are so special, right? So this is the first image taken from James Webb Space Telescope, which is the telescope that we believe probably the best telescope that we ever had up to now to date, and this will surpass the this will go beyond the capabilities of the Hubble Space Telescope, which was the one that we normally believed as probably the best telescope that we have. And from the lessons that you have learned up to now, you probably know that why we have these space telescopes, right? So once you go into space, you are basically avoiding the atmosphere. So which means you can always get clear images for the same technology compared to a telescope on the ground, right? Now in this image taken from the James Webb Space Telescope is actually a very tiny patch of the sky. And what you see here is, as the caption tells you, many of these galaxies that you see here is actually in a galaxy cluster called SMACS 0723, right? And you can see that, of course, these images that you see with streaked lines like this, these are actually nearby stars, right? And almost all the other objects except these brighter asterisk type objects, almost all the other objects are galaxies that you see here. And you can see that there are arc type, arcs type like this throughout the image and each and every place. And this is a special effect called gravitational lensing. So what that means is due to the huge mass that you have inside the galaxy cluster, this can bend light, right? As a result of that, these huge galaxy clusters act as a lens. So you know the lenses that you have used in the laboratories, right? So like that, these galaxy clusters can act as a gravitational lens, which will help you to look at the images or the galaxies or galaxy clusters that are so far away from us, right? So that is called a lensing effect, right? You probably have heard about this. And we will talk a little bit more about this when we go into the section about the extragalactic astronomy. But for the time being, just get this information, and you can see that these images are coming from the billions of light years away, and still you can see like the arms of even galaxies right here, right? Spiral arms, like something like that, one that you see here. And you should get the idea about the capabilities of this telescope then, right? So this is just the first image that they just sent to us. And you probably have seen that other image. And this is, by the way, the Hubble, the most deepest image or the ultra deep field image that the Hubble Space 2. And you can see the difference, right? So this is the image from the Hubble space, and this is a similar kind of image from the new James Webb Space Telescope. So it is more capable of doing things. And just to let you know, the Hubble had a 2.4 meter mirror, and the James Webb has a 6.5 meter diameter mirror. Right? It's not actually a single mirror; it's a collection of small hexagonal type mirrors. But it's the development of the technology, and the larger the mirror, you get more details in your image, right? So that's how you connect this information that you see in the news to what you have learned about the telescopes and the technologies, right? And here is another one, like Let me see it's here or not. Actually, this is called Carina Nebula. This is again a star-forming cloud. So there is a place when you have a cloud of gas. So those are the regions that we used to have, star formation, new stars forming. And this is an image taken from the James Webb Telescope, which we called as the Carina Nebula, which is a cloud of gas that you consider as a star forming region, right? You can see that how clear is these images are, right? Right, so this is the James Webb Space Telescope, by the way. And this is an artificial image of the same telescope, right? So it's just for your information. So let me go back to our regular lesson by stop sharing this. But it is always helpful, just to know what's happening in astronomy, because astronomy is a field that usually get updates each and every day. So you cannot kind of teach the same thing each and every day, right? So you have to get updates, and you always have to, change the things in astronomy, because it's a science that's changing continuously with the new telescopes, new technology, and new findings, because there are so many things that we still do not know, right? So let me share the slides. And by the way, for some reason, my interactive add-on that I used to have to share the slides with you doesn't work in these days for some reason. So that is something that actually out of my control. So because of that, I will directly share the slides with you. Let me start sharing the screen. And I have share my screen. So please let me know if you cannot see my PowerPoint slides, right? And also, whenever you have a question when I am teaching, please feel free to ask, right? So I will try my best to answer for the questions as much as possible. And if I don't know something, and there are certain things that you can figure out yourself in certain ways. If that is the case, I used to point you to a location that you can find the answers, right? Right. So thank you. I can see that all of you can see the PowerPoint presentation. And to start with, now today I am going to talk about the sun, right? Now we have talked a little more information about the sun in the last lecture when we were discussing about the solar system. However, I have decided to include a separate chapter about the sun this time, which I didn't do in the last year. And the reason is actually this is kind of the energy source for us. And we have been, also talking about these renewable energies a lot in our country these days, right? And also about the solar energy, right? Why do we need the solar energy? And I mean, whether it's a reliable source or not. Now, from today's lecture, you will learn that how reliable it is to use the solar energy, right? Because what we are going to learn here is not the technologies about the solar cells, but we are going to learn about the source of the energy, that is the sun. So from here, we will learn about different properties of the sun and different parts of the sun and how the energy is generated inside the sun. And then you will understand that whether it's a reliable source or not. Because if we are talking an energy source that will last only for, let's say, 50 years, then there is no use of talking about it again and again, right? Because after 50 years, you will not have that particular energy, right? And this is the problem we have with the fossil energy, because at some point, the fossil energy will go away, right? Now, you can see that even for us in these days, all the crisis that we have because of this energy problem, right? Now, by the end of this lecture, you will understand, of course, in terms of as an astronomer, you will understand different properties of the sun and how it produces its energy and different parts. those kind of things. And at the same time, you will get the idea how reliable to use the solar energy, right? How long will it last? For example, as I told you, it has to last a very long period, right? If you are going to use it. And also there should be enough energy that we can generate from that for the whole world, right? So if not, there is no point of talking about it, right? So that's in terms of the energy wise. However, we are talking in the perspective of, in astronomy, we are trying to learn about all the properties of this particular object, but it's also important in terms of the energy wise. So let me start with this picture, right? And this is our star, the sun. So this we used to tell that this is our local star as well, because there are billions of trillions of stars in our Milky Way and also inside other galaxies. But for our solar system, this is the only star that we have. Actually, when you compare our own sun with the other stars that you used to have in the sky, there is not much different, right? I mean, this is kind of an average stars in many ways. I mean, even if you talk about the other stars, most of the stars are like this, right? So what is special about this then? The specialty is that this is close by to us. Because of that, we will, and this is the energy source for us, right? So because of that, this particular star is special for us. However, if you get the whole, I would say this whole set of stars as one badge or one group, our sun does not have a specific place in there, right? So this is just an ordinary star, and you will when we talk about the stars, you will learn about it, right? And in this image, actually, you can see some solar flares and coronal mass ejection on the outside. We will learn about that this particular lecture. And the image that you see here is a combination of two separate satellite pictures of the sun, right? So the inner one is from the Solar Dynamics Observatory, and the outer one is from the Solar and Heliospheric Observatory, right? So you can see that there are dedicated observatories to observe the sun and different activities that we have inside the sun. Now, what I want you to explain in this lecture is to explain how the composition of the sun differs from that of the earth. Now, what kind of and how the earth looks like, right? And compared to our earth as a planet, you will learn that why sun is so different than the earth, right? I mean, we will not directly tell you, but you will understand it when we go through the details about the sun, because the earth is something that you know very well about, right? And then also I would like to describe the various layers of the sun and their functions very briefly. So that means there are different layers of the sun. Like I told you, there is a corona, and then inside that there is a different sections inside the sun. So we will learn about those, and also we will try to explain at least very briefly what happens in these different parts of the sun's atmosphere, not in detail because we do not have time, but very briefly. And then there is something that is important for us, that is the sunspot cycle, right? So in more generally, we used to tell as a solar cycle. So there is an activity called solar sunspot, and there is a cycle for that happens again and again. So we will talk very briefly about that. And then this part, explain what space weather is and how it affects to the earth. So the reason that we talk about the space weather under this particular topic is that the space weather that is affecting for us is mainly due to the different activities of the sun, right? So instead of talking a whole lot about space weather, I have a small section in the book as a reading assignment for you. You can go through it and read it, right? But I will give a very brief introduction. And the last one will be trace the nuclear reactions in the solar interior. The reason for discussing about this is that the main energy source, or the main energy generation method inside the sun, also in for any other star, is these nuclear reactions, right? So which is important, and because of that, we will try to understand the basic nuclear reaction that happens inside the sun, which will lead to generate all this energy that we are having, right? Right, to start with. So let's start with the structure and the composition of the sun. And as I told you, the sun, like all the other stars, is an enormous ball of extremely hot, largely ionized gas shining under its own power. Now, including sun and all the other stars, the specialty about these stars is that they actually shines from its own power, right? So they don't get the help of any other object. So they are kind of energy sources basically, right? And in terms of the size, you can see that here is a small part of the sun right here, and I have drawn the size of the earth right here for you to compare the size of the sun to the size of the earth, and you can see the size differences, right? The earth is very, very tiny compared to our sun, right? And actually you can't see the entire sun here, but there is an inset image right here to show the entire picture of the sun. But this is for comparison to, and understand how small is our earth compared to the sun, right? Now, if we talk with numbers, the sun could fit 109 earths side by side across its diameter. So in terms of the diameter, basically that means the diameter of the sun is 109 times larger compared to the diameter of the earth, right? And if you take in terms of the volume, you can actually include 1.3 million earths inside the sun, right? You should understand now how huge is our sun, right, in terms of the size, right? And the other important thing about the sun is sun does not have a solid surface or continents like Earth, nor does it have a solid core. So it doesn't have, the solid surface, right? And let's see what we have inside the sun, right? So so there are some characteristics that we can. You don't have to remember these things, by the way, right? So there are certain things that is always helpful to remember things, but I will mention those. One thing is the distance to the sun is approximately 1 astronomical unit. I think I have mentioned you what is an astronomical unit within the first two lectures. That is basically the average distance from our Earth to Sun. And if you measure it, it's around, a huge number in terms of the kilometers. But if you get it as an astronomical unit, that is defined as 1 astronomical unit, right? And there are other parameters that you can read here. For example, the mass is 1.99 times 10 to the power 30 kilograms. And that means this is compared to the mass of the Earth. This is 333 times 400 larger, approximately, right? And you have the angular diameter, which is roughly the same angular diameter that you have for the moon, that is half a degree. And like that, you have the mean density, 1.41 grams per cubic centimeter, and then gravitational acceleration at the photosphere. I will show you what photosphere means. And then there is something called solar constant. And then the luminosity, that is something that is important. The luminosity of the sun is 3.8 times 10 to the power 26 watt, right? So this is the energy that it generates basically. And the spectral class for the sun is G2V. Now, just to explain you what this spectral class means, is that for all the stars that you see up in the sky, I mean, even for the stars that you cannot see, we used to take the spectrum of the stars, right? And depending on the nature of the spectrum, we used to divide all the stars into different spectral classes, right? And so these spectral classes are basically based on the temperature of the stars, and we will learn about all these things in our next lecture. And based on those information, we have given a spectral class for the sun, and that class is called G2V, right? And then the temperature is around 5,800 Kelvin. So that is the effective temperature. And then rotation period at the equator. So you can see that it has a rotation period mentioned specifically at the equator, 24 days and 16 hours. So that means you should understand that when you go beyond the equator of the sun, this rotation period may change a little bit, right? Right. And then what do you have inside the sun? Like whether you have hydrogen, helium, or whether you have iron, what kind of things that you have inside the sun. Now, most of the available gas inside the sun is actually hydrogen. In fact, more than 90% of it is hydrogen. And then you have some helium. And of course, you have other elements like carbon, nitrogen, oxygen, magnesium, iron, those kind of things, but very little amount, right? And this is not only true for this particular star, but most of the stars in this range or with these features, you basically have most of the time hydrogen inside that and little amount of helium. And you will see why is that in our next lecture when we start talking about properties of stars. Right. Now, in 1920s, when it goes up to the 1920s, nobody knows actually what kind of elements that we have inside the star. And it is this lady astronomer who she did her doctoral thesis or the PhD in 1925. So she led the foundations for understanding the composition of the sun and the stars, and she was the one actually who first mentioned that most of the material or the gas inside the sun is hydrogen and helium, but nobody actually believed that at that time. But what we know now is most of them are actually hydrogen and helium, right? And the other thing is the sun is, it's an object with a hot object with huge temperatures, and because of that, most of these elements found in the sun are in the form of atoms with small number of molecules, right? Basically, all of them are in the form of gas, right? So the reason is that sun is so hot that no matter can survive as a liquid or solid. When the temperature increases, everything becomes a gas, right? That is the idea. And the other thing is sun is so hot that many of the atoms in it are ionized. So what happens when the temperature increases, the gases get ionized. And because of that, most of these atoms are ionized. And what that means is there are electrons that are stripped off from these atoms, right? So there should be free electrons, right? Now, as a result of that, this removal of electrons from the atoms means that there is a large quantity of free electrons and positively charged ions in the sun, right? So this makes an electrically charged environment, and we used to call that these kind of environments as the ionized gas or plasma, right? So this is roughly what you have inside the sun. And in the 19th century, scientists actually observed a specific spectral line at 530.3 nanometers in the sun's outer atmosphere, right? Now, this sun's outer atmosphere is what we called as the corona of the sun. And I will show you a picture in the next slide. And so they have observed this specific line, 530.3 nanometer line, in the sun's outer atmosphere. And what they were excited about this is this particular line had never been observed before. So it was assumed that this line was a result of a new element found in this corona, and they call this as coronium at that time, right? However, later these astronomers discovered that this emission line is due to highly ionized iron with 13 of its electrons stripped off, right? So they initially thought that this is a completely a new element at that time. However, later they identified that this particular line came as a result of this highly ionized iron, where there are 13 electrons has gone away or stripped off, right? Now, this is how they first discovered that the sun's atmosphere had a temperature of more than 1,000,000 degrees. From this ionization, they can get an idea what kind of temperature that it should have, right? Right. Now keep having all this information in your mind. This particular image basically explain or summarize all the structures that you have inside the sun, right? First, you have the core right here, and then there is this is called the radiative zone, and then you have a convective zone, and then you have a photosphere and a corona, right? And of course, there is a chromosphere, and then there are something called sunspots that we will talk separately. And basically, this is how the interior or the structure of the sun, right? Right now, if we talk about different layers that we have inside the sun, the core is approximately 20% of the size of the solar interior, and approximately around 15 million Kelvin in terms of the temperature. And that is, of course, the hottest part of the sun. So that is the core is at the center, right? So that's obvious, no? Center region should be the hottest one. And above the core, there is a region known as a radiative zone. That's because the primary mode of transporting energy across it is the radiation, that is this region right here. So you have the core with that 15 million Kelvin in terms of the temperature. And then you have this radiation zone after that, which is responsible for transferring energy using radiations. And then there is a convective zone, which is the outermost layer of the solar interior. So it's a thick layer, approximately 200,000 kilometers deep, that transport energy from the edge of the radiative zone to the surface through giant convection cells. And you can see these convection cells that is drawn in this picture. So basically this part is around 200,000 kilometers long, and it is the section that is responsible for transferring energy using convection, right? So whatever the energy that comes here through the radiation will be transferred through this region using the convection method, right? So that's the interior region and the radiative region and the convective zone. So we have talked about the core and the radiative zone and the convective zone, right? Next, we have to go for the photosphere. Now, if you go to this diagram, the photosphere is the one that I have mentioned here, right? As the next one. Now, the photosphere is a layer that sun becomes opaque and marks the boundary past which we cannot see. So that means when you try to use a solar telescope or something like that to look at the sun, this is the layer that we can see. Beyond that, it is opaque. So that means you cannot see beyond that, right? And so basically the solar atmosphere changes from almost perfectly transparent to almost completely opaque in a distance of just over 400 kilometers. And it is the thin region that we call as the photosphere, right? So that region is called as the photosphere, and I have seen, shown you a picture here. Once again, so there is this the image of the Earth. Just put here to get an idea about the size difference of the sun and the Earth, right? And basically this photograph actually shows the photosphere of the sun. That is the visible surface. And there is something called sunspots in this photosphere. So right here is the sunspot. So this is an enlarged version of those sunspots. And when you look at the sunspots, even today, if you have a good solar telescope, by the way, never ever look at the sun from your naked eyes, right? So that's kind of a general advice for everyone. And I hope you know, I mean, you will not do that as university student, but just to keep in mind, never ever do that, right? Especially as students who did an astronomy course like this in the university, right? So when I say when you look at the sun, that means you have to look at it through a proper method using filters and relevant telescopes, right? You should not look at the sun from the naked eyes, right? That is the primary thing here. And when you look at this through a telescope, you would see these dark areas. Actually, it looks dark not because it's kind of a place relatively cooler uh, compared to the temperatures of the sun. It is actually cooler, but not that much cooler to tell that it is really cool, right? So what happens is typical temperature at the center of this large sunspot is about 3,800 Kelvin. You can see that it's a really high temperature, right? However, the photosphere itself has a temperature around 5,800 Kelvin, right? Remember this 5,800 Kelvin I mentioned as the temperature, as the effective temperature. So, so in around this region in the photosphere, you have 5,800 Kelvin, and with relative to that, the temperature of these sunspots are actually 3,800 Kelvin. So that's why they look in black in color or the dark in color, right? It's because of the relative temperature difference, right? These are actually some images that I am not going to explain you everything here. You can just read through the caption and see what it means. So this is the photosphere, and what we know is the photosphere is the layer that sun becomes opaque, and at the same time you can see these sunspots inside on the photosphere. And after that, we are going to look at the chromosphere, right? So if you go to the previous image right here, you have the photosphere right here, and then after that, next layer is the chromosphere. So that's what you see here. Right? So let's see how the chromosphere looks like, right? The region of the sun's atmosphere that lies immediately above the photosphere. So whatever you have above the photosphere, that layer is called the chromosphere, right? Now, the problem is actually the chromosphere was visible only when the photosphere was concealed by the moon during a total solar eclipse. Now, this is one reason why total solar eclipses are important, right? By the way, this is only relevant when you are looking from Earth, right? So it's a different story if you look at this from the space. But in general, you will not see the chromosphere. However, in a total solar eclipse, because the photosphere is completely covered, then you will see the effects coming from the chromosphere, right? So that is the time where you can see the chromosphere, and because of that, the solar astronomers, especially the astronomers who are working on just doing research about the sun, they always try to observe the chromosphere during solar eclipses, right? Because you can get a lot of details about the chromosphere at that time. And this particular image right here is a composite image with the three components of the solar atmosphere. That is the photosphere, and then the chromosphere, and then the corona is the next one, right? And so you can see the corona is just outside the chromosphere. So you have the photosphere, chromosphere, and then you have the corona right here, right? So let's see what corona is. We will talk about that later, but if you go back to this chromosphere, the observations made during eclipses, as I told you, show that the chromosphere about 2,000 to 3,000 kilometers thickness in terms of the thickness, right? Now, all these details are obtained during solar eclipses, and the spectrum of this chromosphere consists of bright emission lines indicating that this layer is composed of hot gases emitting light at discrete wavelengths, right? So once you get the spectrum of this particular region of the sun, you get bright emission lines that shows you that there are hot gases, right? And one important thing about the chromosphere spectrum is that there is helium lying inside there, so which tells you that the helium is available, right? And one thing to note here is actually the chromosphere is hotter than the photosphere, right? So you have the chromosphere. Normally we used to tell that what is inside should be hotter, right? Because energy is transferred towards the outward region. But here there is an exception for this one. If you compare the photosphere and chromosphere, actually chromosphere, which is the outer region, is hotter around, that is means around 10,000 Kelvin than the photosphere. So that is something special, right? Now here is the temperature variations of the different regions inside the sun. You can see that photosphere is right here, and when you go to the chromosphere, then what has happened was the temperature has increased. And not only that, after the chromosphere, when it goes to the corona region, which is the next region, next outer region that we are going to talk, the temperature has even increased more, right? And there is a region called transition region, right? So there is a sudden jump in the temperature when you go to the corona region, right? And so that's what I have mentioned here as the transition region. And what this graph shows you is the temperature increasing of different regions, right? And what is prominent here is actually the sudden increase in the temperature when you go to the chromosphere to the corona region, right? And also from photosphere to the chromosphere, right? Until that, actually temperature keeps decreasing. You can see it, right? But from here it keeps start increasing. Now, in 2013, actually NASA launched a satellite, so which is called Interface Region Imaging Spectrograph, or IRIS in short form, to study this transition region to understand how and why this sharp temperature increases, right? Right. So this is one of these portions, the transition regions, an image taken from this particular satellite that I have mentioned you. Just read through the caption right here, right? So I'm not going to, explain one by one, but you can go through the caption and see what I have mentioned here. Right, now the last one is the corona, right? Which is the outermost sun's atmosphere, which we called as the corona. And like the chromosphere, the corona was also first observed during a total solar eclipse, because that is the time that you can easily observe these regions, right? Because all the other sections are covered. However, this is not relevant if you are observing from the space, right? So that's, you can observe it always. And this corona extends to millions of kilometers above the photosphere and emits about half as much light as the full moon, right? Now, corona is extend for millions of kilometers, and basically, actually, corona extends so far it actually passed the Earth as well. So basically, we are living inside the corona of the sun, right? And also it emits light comparable to the full moon, right? Half of that, if you take the corona only. Right? And this is called a corona graph. Corona graph means, as you see here in the caption, this image of the sun was taken on March 2nd, 2016. The large dark circle in the center is the disk that blocks the sun's glare, allowing us to see the corona. Because if you try to see the complete sun, then the corona is not clear, right? Because it, the light coming from the central region outperform all the other regions, so that you cannot see anything because of the glare of the light. And because of that, you close the inner region and then look at the corona. Right? And inside the corona, there is something called coronal hole actually. So that's what you see right here as a dark region. Basically, as I told you before, for the sunspots as well, these coronal holes are relatively cooler when you compare to the other region, right? Right. Now, the next thing that we should talk about the sun is the solar wind, which is basically one of the main factors that affect our solar, the space weather, right? The solar wind means actually when you talk about the sun's atmosphere, the atmosphere has this ability to produce stream of charged particles, right? And these charged particles are mainly protons and electrons. So the sun can produce a stream of these charged particles, right? And this is what we called as a solar wind. So we called as a solar wind, but what actually happened is inside solar wind means this production of stream charged particles, mainly protons and electrons, right? And the reason actually the existence of the solar wind is because the gases in the corona are so hot that moving so rapidly that they cannot be held back by the solar gravity, right? The gas is so hot and you get free electrons and those kind of things. And this gas is moving here and there very rapidly. And because of that, the gravity cannot hold everything towards the sun, right? Because of that, you will get the solar wind. And the solar wind actually basically come from these coronal holes where gas can stream away from the sun into the space by unhindered magnetic field. The sun itself has a magnetic field, but what happens is inside this, when you come to these, excuse me, to the coronal hole region, this magnetic field get extended a little bit towards the outward region. So this will help to escape all these charged particles that comes as a solar wind, right? Now, when you talk about the surface of the Earth, we are usually protected up to some degree by these solar winds from the Earth's magnetic field. Everybody knows that we have a magnetic field for the Earth now, right? From this magnetic field, we are protected. Right? However, if you remember how the magnetic field looks like in the Earth, when it goes towards the north and south poles, magnetic fields are, bending towards those two poles, right? And because of that, these charged particles that are accelerated by the solar wind can follow these fields down into our atmosphere, right? So this is specifically applicable to the regions that are close to the north and south poles of the Earth, right? Now, what actually happens is when these charged particles strike these magnetic fields, they will actually get excited and move into these higher energy levels. And once they go into the higher energy levels, they cannot, be in those excited states forever. So the normal thing is they will again go into these de-excited levels by releasing energy, right? So depending on which energy level that they are initially, so they will release different kinds of energies, right? Now this will actually make a very beautiful phenomena that we can observe from the Earth. and this is called auroras, or northern or southern lights, right? So you may have heard about this, and this is a picture of an aurora. Uh, a colorful glow in the sky result from the charged particles in the solar wind interacting with Earth's magnetic field, right? Uh, this is a picture actually taken from the Iceland in 2013, right? Now you may be wondering that why we cannot see auroras, right? The reason is actually, I have given you the reason already. This Earth's magnetic field actually bended towards the poles when you go to either North Pole or the South Pole, right? So because of that, these charged particles interact with this magnetic field in the North and South poles because they are very close to the Earth. And then what happens is they get excited and move on to the higher energy excited states and then release their energy coming back to lower states. Now it is this releasing energy uh, correspond to different wavelengths which make this nice pattern on the sky, right? So, if you want to look at or observe the auroras, then you have to go into either countries like, Alaska, Iceland, those kind of countries. Even for the northern part of the USA, these are regularly visible. I have seen this few times, which is a very, very beautiful event. However, you have to, be on alert and be patient for a long time to look at these kind of events at night, right? And there is actually a website that predict these auroras, right? So if you go and search in the internet, you can look at it. If it becomes very, very strong, sometimes very rarely you can see it to the countries in lower latitudes. But I have never heard that somebody have observed something like that in Sri Lanka, because if we are to observe it, then everybody else in the world should be able to observe because we are very close to the equator, right? Right. So that is one phenomena that you can see due to these charged particles on the magnetic charged particles interact with the Earth's magnetic field. Right. Now let's look at this solar cycle and sunspots. Right. Now the first evidence that the sun changes came from studies of sunspots, which are large dark features on the surface of the sun caused by increasing magnetic field, right? Uh, so because at like 100 to 200 years ago, we actually did not know whether the sun changes or sun sits like that forever, right? But by studying these sunspots in the sun, we now know that the sun changes from time to time, right? Now the reason actually that we have these dark features, which we called as sunspot, that we see from time to time on the surface of the sun, is due to the different magnetic activities inside the sun, or increased magnetic activities at different times, right? Now, as you saw the sunspots in previous images, they'll actually look darker because the spots that you see as sunspots are typically lower in temperature compared to the surrounding region, right? Uh, Actually, there are certain occasions that these sunspots become larger enough to visible from the unaided eye. Now, keep in mind that when I tell you unaided eye, that doesn't mean that you are looking at directly from the eyes, right? So unaided eye means if you have a method or mechanism to look at the sun directly, then you should be able to see some of these spots from the naked eye as well, right? Probably one way to look at from the naked, just not from the naked eye, is look at use a solar filter, right? So there are specific piece of glasses that you can wear on your eyes and then look at the sun, right? Actually, many of these sunspots are even larger than the Earth, right? even some of these larger sunspots sometimes reach to a diameter over 140,000 kilometers, right? So it's obvious now, you can compare to the size of the sun, these sunspots also can be huge compared to Earth. Now, uh, Galileo in 1612, we have now talked about Galileo a few times because he was the one who invented the telescope as well. By recording these apparent motions of these sunspots, we can actually, Galileo derived actually, the sun rotates on its axis with the rotation period approximately 1 month, right? So which means for each month, the sun used to rotate or complete a one circle, right? So that this is found by Galileo Galilei in 1612 by observing the motion of these sunspots, right? So that is one of the major findings from the sunspot. Now, from the modern observations, what we know is that the speed of this rotation. Now, I have the Galileo has told that roughly take 1 month to rotate for the sun. The speed of the rotation of the sun varies according to the latitude. So that means when you go towards more north or towards more south from the sun's equator, the rotation period is about 25 days at the equator and 28 days at the latitude, 40 degrees. And it's become 36 degrees at the latitude of 80 degrees, right? And we have a specific name for this behavior, which we call as differential rotation. So that means at different latitudes, you have different rotational speeds, right? This is called differential rotation. Here is an image of the sunspots, which are taken around 2012 in July. That is exactly 10 years ago now, right? So it's also the month of July. Right. So anybody have any question up here before I move on to finish the last section? Right. So let me just explain a little bit more about this rotation. And this is one of the examples by taking this image of the sunspots at different times. As you can see, it's starting from 2001, March 26. By the way, when you see these dates, it should be 2001 and then day and the month. Right? It's kind of weird for maybe weird for you, but this is actually the US system of writing the date and time. So they used to write the month first and the day second and the year after that. So it's kind of, I mean, in the sense of what we are doing here, it's kind of weird, right? There is no order for that, but that's how they write the date. And you can clearly see that the change on the location of the sunspot from day to day, which gives you an idea that, and also you can get an idea that the sun is rotating and also the rotation speed and all these kind of things. Right. And then there is something called sunspot cycle, right? So before I go into this lecture series, there is a link that I would like to show. I assume that, I don't know whether you can see this. Let me reshare the window so that we can see it, right? Right. So this is, if you look at, we have been talking about the sunspot. You can see that here is a graph. On the x-axis, you have the dates starting from maybe somewhere like 1600 So 1700 up to 2000 and up to 2000, close to 2020, right? 2018. Those are that's at the time. And then on the y-axis, you have the number of sunspots, right? And you can probably see a nice relation here. So there are maximas and minimas in this image. So what that means here is, and this happens periodically, right? So the sunspots become maximum at certain point, and then go to the minimum, and then to the maximum, minimum, like that. Number of spots that you can see in maximum is different in at different times, but regardless of that number, what you can see is there is always a maximum and a minimum, like that, right? So this goes as a cycle, right? So this is real data, and you can also check it, the real data as well, and you can clearly see that if you count number of sunspots, there is always a maximum and minimum that happens periodically, right? Now, let me go back to the presentation again, right? Let me share the screen with you, right? So that is right. So I hope you can see the screen again. That is called the sunspot cycle, right? And you can see very clearly from the observational data, there is the maximum, minimum, like that. This sunspot cycle goes on. Now the data is for like for 200 and more than 200 years. So we can confirm that this happens, right? So the between 1826 and 1850, there is a amateur astronomer called Henrich, who found that the number of sunspots varied systematically. So that's what I showed you from that graph. And this sunspot cycle is normally what he have observed is it's a decade long. So approximately 10 years you get a maximum, and then after 10 years you get another maximum, like that. So what he have observed is that the total number of visible, I think they should be sunspots on the sun at any one time was likely to be very much greater at certain times. So which we call as the periods of the sunspot maximum, and then at other times the periods of the sunspot minimum, right? So which means that sometimes it become maximum and then they become minimum, right? So I hope as I showed you the real graph, you should understand what I'm telling here. Now we know that this sunspot maxima normally occurs at an average interval of 11 years, right? Usually it happens for every 11 years, and the intervals between the successive maxima have a range from as short as 9 years to the 14 years. So its average is 11 years, but it could go as low as 9 years, so up to 14 years, right? So that's the range, kind of the range that you have. Now, during this sunspot maximum, usually you get more than 100 spots, as you saw in the graph. It should be more than 100 spots, right? So when I upload this lectures to Google Classroom, you can just click the link and go and look at the graph, right? So it will directly show up the graph. Even there are 100 spots, if you take in terms of a percentage of the area that is covered from the sunspot in the sun, it's actually less than half of 1%. Right? It's like 0.15%, right? So it's a very small area still. Right? In the sunspot minimas, when you do not have any, when you have the minimum, that means sometimes you may see few sunspots and sometimes maybe no spots are visible at that particular time as well, right? Now, if we talk about the recent history, in recent history, sun's activity reached its maximum peak or the maximum of the sunspots in 2014. So now it's 2022. So the next 3 or 4 years, we can expect another maximum break, right? Now, so I would like to very briefly mention about this relation between the magnetism of the sun and the solar cycle that I have mentioned. So there should be a reason for this now to happen, these maximum and minimums of the sunspot cycle. What we now understand is that the sun's changing magnetic field is the one that drives these solar activities, right? So we all know that sun has a magnetic field. So what happens is uh, you can actually measure the solar magnetic field using the property of atoms, and this specific effect that we are using to measure the magnetic field is called Zeeman effect. And if you search this in the internet, you may find what Zeeman effect means. And if you have done enough of quantum mechanics, you may have learned about this as well, but I'm not sure. But the basic idea is, you know that you have one emission line sometimes. Let's say you have hydrogen emission line in a spectrum. However, if this particular environment or the line is presented in a magnetic field, this magnetic field can split this particular line into sub lines, different lines that have differences in small energy, with small energy differences, right? And that this particular effect is we used to call as the Zeeman effect. And this mathematical calculation, everything can be done using quantum mechanics. This measurement of the Zeeman effect can be done using a spectra. So measurement of the Zeeman effect in the spectra of the light from the sunspot region show them to have a strong magnetic field. So this is what we have, right? So when you take the light from these sunspot regions, we can see always strong magnetic fields, and then there is a polarity correction between these magnetic sunspots and the magnetic field as well, which I would not talk here, but this is the Zeeman effect that you can read through it, and this is how the magnetism and the solar cycle is connected. Actually, I do not expect to go into too much details in this region. However, I have put the images that are in your book, right? So what if anybody can need more reading, what you can do is go into the book, and these images can be located, and around the image there is a story that explains all these images, right? So that's why I didn't remove the images from the PowerPoint presentation, so you can trace back to the book and read it yourself. So different features about the solar flares and all these things, and also some information about the coronal mass ejection, which we did not talk too much. And here is how a solar cycle looks like. You can see that it started from 1996, and the activities has increased a little bit. So that's why you can see these white spots, and then it decreases again when you go into 2006, right? Right. Now you can see that there is always an effect from the activities on the sun to us, right? The best example is the solar wind that comes to our atmosphere, right? Now we have in our Earth, we have a different setup now. Our technology is now developed. We have a lot of satellites on the space, and astronauts are taking long-term residencies in the international space. And we as millions of people are using cell phones, GPS, wireless communication, those kind of stuff, right? Now, because of this, so we are using electromagnetic spectrum each and every time. So this means we have to be careful with the solar wind and those kind of things. So we should predict in advance that these things are coming, right? Now, this is why the space weather comes into play, right? Otherwise, you may be wondering why do we even worried about the space weather, right? Because we are not in the space now. But the problem is we get the effect, right, from these different phenomena that happen inside the sun, especially the sun. I mean, you get actually meteor impacts and those kind of stuff as well, but the sun is the one that is more important for us because there are stories about the destroy of these different communication systems due to these different effects coming from the sun at certain times. And because of that, we have this separate section called space weather, that we have different satellites that used to monitor the sun and predict different activities, right? Now, there are some more information in this section 15.4. You could always go there and read about it, right? So I have the images here. Right. Now, I want to go into the next section about the sun to very briefly talk about the as the energy source, right? We talk about different sections and different layers of the sun and what happens inside each layer, those kind of stuff. But apart from all these, information that we have inside the interior of the sun, what we know about the sun is, even if you go outside, gives you enormous amount of light and energy, right, in our day-to-day life. Right? Now, it is very important for us to know how this energy is generated inside the sun, right? This is specifically important to understand whether it is sustainable or whether this energy will probably finish within next 5-10 years. So we need to know about these things, right? So that's why it is important to understand what happens inside the sun for the energy production, right? Now, to understand that, again, you need some physics, right? Especially about the nuclear reactions. Now, for the nuclear reactions, there are typically two types of reactions: fusions and fission, right? Fusion means there are two light atomic nuclei joined together to form a heavier nucleus. So when this happens, some energy is released, and you can use that energy. And on the other hand, when you have a heavy nuclei, which is break up into two elements which are lighter, then again the energy is released, and these are called fission reactions. Basically, this is what happens inside the nuclear reaction, right? Now, this is specifically important when you talk about the interior of the sun, right? Now, what happens deep inside the sun, that means that core region, is that there is a 3-step process that takes 4 hydrogen nuclei and fuses together to form a single helium nucleus. So this is what happens inside the interior of the sun. And of course, this happens in each and every star if they have the required properties, right? Most of the stars will go through this particular process, but we will learn it here because we are specifically focusing about our sun. And if you take the mass of the helium nuclei compared with the mass of the 4 hydrogen nuclei, what we know is the helium is slightly less massive compared to 4 hydrogen nuclei, right? So which means there is a mass difference when you go from hydrogen to helium. It is this mass difference that will be converted into energy. You know this equation called E = mc squared. Using that, you can always convert mass into energy, right? And this is what happens there. Now, so let me go into the diagrams directly. And there is a mechanism that works inside the interior of the sun for this to happen. That means to convert hydrogen into helium. And as you saw in this initial table, most of the elements that we have inside the sun is hydrogen, right? So you basically have 2 hydrogen fusing together to produce H2, and this is also called deuterium. And during the process, there will be a neutrino and positron going out. from this particular step. This is the step 1, and this whole step, whole process is called proton-proton chain, right? So that is a specific name for that. And in step 2, now remember that we have H2 right here, and you take that H2 and then you combine that with another hydrogen. So deuterium combined with the hydrogen, and from this combination you will have a new atom right here, He3, and during the process there will be a gamma ray that is going out, right? So this is the second step in this proton-proton chain. Now you have He3. Now once you have large number of atoms like this, you will have many of these He3s at the end, right? So this is basically an isotope of the helium, but not He4, right? And so what happens is then, as I told you, there will be many of these things at the end, because this is not you have a single atom, then you have only one of these processes. This process, it happen in large scale, right? So 2 of these He3s will combine together to make the final alpha particle of the He4, and during this process, 2 hydrogen nuclei will go away, which will again combine to the similar process, again, right? And this is the step 3 of this proton-proton chain. And if I summarize everything, this is how hydrogen is converted to helium. So there are 3 steps: this first step, second step, and the third step, right? And this is what I have shown here. This is the first step, and this is the second step, and this is the third step to convert hydrogen into helium, right? Now, why this mechanism is important inside the sun is because of this, right? So you can simply calculate the amount of energy generated from this simple process. So basically what happens is 4 hydrogen atoms. 4 hydrogen will become 1 helium. So if you take the mass of initial hydrogen atom is 1 point this much. And you know what is U, right? So it's a unit for the atoms. And then you get this number for 4 hydrogen, and then you use the mass of the helium, it is this much. And once you take the difference, when hydrogen is converted into helium from this process right here, that means the hydrogen, 4 hydrogen atoms will be converted into helium at the end. And this is the amount of energy, sorry, the mass difference that you have at the end, right? So that mass difference will be released as an energy. Now, if you, so I have mentioned here that the mass lost is 0.0862 U, and that is roughly 0.71% of the mass of the initial hydrogen atom, right? Initial hydrogen atom mass is this one right here, and if you take the percentage, this is just a very small amount, right? 0.71% of the mass is lost. However, this mass will be converted into an energy, right? Now, if you think about this amount, the loss of this amount of mass, that is a 0.71% of the mass of the initial hydrogen. So if you take the 0.71% of that mass of initial hydrogen, that will be, if you take 1 kilogram of hydrogen is converted into the helium, then the mass of the helium is only 0.9929. So the rest of this small amount, that is 0.71% of that kilogram, will be converted into energy. So for 1 kilogram of hydrogen, this much of kilogram, 0.0071 kilogram, will be converted into energy. Now let's see how much of energy we can get from this particular amount, right? So you get that amount and convert it to energy by using E equal mc squared, right? And you will see the amount of energy that you get from 1 kilogram of hydrogen is 6.4 times 10 to the power 14 joule, right? Now this amount, the energy released when a single kilogram of hydrogen undergoes fusion, would supply all the electricity used by the typical US household for roughly 17,000 years, right? Actually, this is not directly related to astronomy. I mean, what you need to understand is how much energy that the sun can generate, right? Just a 1 kilogram of hydrogen. It's a tiny amount when you consider the whole complete mass of the sun, right? So 1 kilogram of hydrogen can generate this much of energy that will be enough for whole country USA, which is a very large country that, you know, not like ours, uh, to use for all the houses in the USA for 17,000 years. So now you can understand why people are interested about the solar energy, right? Solar energy is, you know, it's widely available. Like, I mean, there is no end to that, right? So we cannot even see that it's going to end in recent past, right? Because there is so much hydrogen. Now, what we know is the luminosity of the sun is 4 times 10 to the power 26 watt, right? Which is 600 million tons of hydrogen you have to convert into helium for each second, right? Of which 4 million tons are converted from matter into energy. So we know that the luminosity is 4 times 10 to the power 26 watt, right? So that means per 1 second, you have to convert 600 million tons of hydrogen to helium to achieve this much of energy, right? I hope you can understand this, right? So what we have discussed here is what amount of energy released by converting 1 kilogram of hydrogen into helium, right? However, we know that the luminosity of the sun that we currently experience is 4 times 10 to the power 26 watts. That means in order to achieve this number, you have to convert 600 billion tons of hydrogen into helium for each second, right? For each second. So that means you have to convert huge amount of hydrogen. Even though this number is very large, uh, the store of hydrogen that you have inside the sun is so enormous that you can do this for another billions of years, right? I mean, if I remember, this will happen for another 5 billion years, if I remember, right? So, which means this confirms that using solar energy for anything will do no harm, and this is probably the most reliable energy source that we have, right? Because this fossil energy, they are going to end, right? So they are on the earth now, but if something like extraordinary doesn't happen, we have more than required energy that's coming from the sun, and this is why using solar energy is important, right? And uh, this is actually, now I showed you what is the process that convert hydrogen into helium inside the sun. However, there is another method that you can convert hydrogen into helium. This first method is called proton-proton chain. And for any star that has a mass of smaller than 1.2 times the mass of our sun, will produce the energy using this method. So that means using the proton-proton chain. And in short, we used to tell that it's a PP chain, right? Because it always have two protons combined together to form this helium. At the end, actually, there are four hydrogen atoms. However, when you have stars that are a little bit higher in mass, that means also the hotter in terms of the temperature, and you will understand why I am till that hotter stars are higher in mass in the next section, right? There is a separate cycle or a separate way of converting hydrogen into helium that is called CNO cycle, or the carbon, nitrogen, oxygen cycle, which will basically accomplish the same result, right? So there is no difference, but mechanism is different, right? And this is how it happens. You have the hydrogen, and in this, when the mass increases, you have a little bit of carbon as well. So it will go through this mechanism. Basically, you input hydrogen and then you will get helium. But in between that, you will get involved carbon, nitrogen, and oxygen. So that's why we used to tell this as a CNO cycle, right? However, just keep in mind that you don't get carbon or oxygen at the end. So you will put hydrogen and it will be converted into helium at the end. But during the process, you have carbon, nitrogen, and oxygen. So that's why we used to tell that this is CNO cycle, another method of converting hydrogen into helium inside stars. Now, which method is more applicable is actually depend on the mass of that particular star, right? For example, and there are two curves here in this diagram. This x-axis is temperature and y-axis is the amount of energy production. And you can see that for the sun is in this yellowish curve, and for this temperatures up to 15 million Kelvin, you can see that this yellow curve is relevant to the PP chain, and this green curve is relevant to the CNO cycle, right? So what you can see is up to 15 million, around 15 million Kelvin, PP chain is the primary method of generating energy, right? But what happens is when you go into the higher temperatures, for example, 25 million to 30 million Kelvin, what would happen is the energy conversion from PP chain become less effective and the CNO cycle goes higher. So which means for these stars with higher temperature, you will understand that when I tell higher temperature stars, most of the time they are the stars with more massive. The mass is larger for those stars, right? They will use the CNO cycle to convert hydrogen into helium. So that is the difference between the CNO cycle and PP chain. And this is not only important for this particular star, our sun. This is always common to all the other stars as well. And you will see it in the next chapter, right? Right. So this is the end of this particular section about the star and our sun. So I would, during this half an hour, I try to, summarize as much details as possible about the sun. But I know that I didn't give you all the details, but I have directed using images and reading assignments to read through some of these sections. What is important here is these reading assignments are very important, right? So I have not asked you to read the whole book, right? So in the last lecture and this lecture, I have given you small sections in the book, right? Now, if any of you is not familiar with the book, let me just give you the section, the link to the book as well, right? I mean, this has directly the chapter there. But if you go to this site, you can download the book and you can read the book as an online version. And also there is a app called OpenStax. I have given you at the beginning. You can download that app and then get the book to that app and read it to the app as well. So there are a number of methods and this is completely available for free for anyone. And it is completely legal to use it. So anybody can use it, right? Because of that, there are no excuses for you to not to read it. So especially these reading sections, when I assign something from the reading sections, I expect all of you will read it. If anybody has a question after reading it, okay, this part is not clear, can you explain? Then I will explain, right? Other than that, my assumption is all of you know about that particular section, right? So I will upload this to the your Google Classroom as well. Let me so within next 1 or 2 days, I will upload this. Anybody have any questions from today's lecture? Right, if not, just to update you, you will have your in-class examination, which will consist of a number of MCQ questions. And this will happen in a date somewhere between 20th and 30th, right? In between those kind of date, and everything that you have learned up to that date will can appear in that exam. right? So that's how it works. And it's probably like a 45-minute thing maximum, right? And maybe 15 to maybe 20 MCQ questions. So that's how it works. But everybody who participated for the exams and go through the notes, you should not have an issue facing for such an exam. And if you do not have any questions, I'm going to stop from here. Next lecture will be again on tomorrow morning, right? Just to let you know, because I want to finish it, by early next month. So we have completed almost half of the lectures now. Now the next section that I am going to start is actually about the stars, right? So remember, we have now gradually going into these different sections. Now we have completed today talking about our solar system. Now the next set of lectures will be about the stars, and then we will move on to galaxies, right? So make sure that you participate the next one, because we are going to talk about the properties of the stars, and we will talk about different calculations and what kind of properties that we are talking and how you talk it in terms of equations and like, for example, how to measure the brightness of a star, those kind of things, right? Right, then thank you for participating for the lectures. If you do not have any questions, let me stop the lecture today.